So let's start. I want. So yesterday I tried to show some examples of how to use shuffle operands to show that some left-right modules over operands are free, and then you can infer some consequences. So let me start with a small illustration of what methods are there to, before doing all these huge diamond lemma computations, it's good to kind of decide for yourself what you believe in, whether some module is or not. Let me give you some very easy numerical criterion that can give you some estimates. That would help you decide whether you want actually to bother with all these computations in a given particular situation. So numerical test for freeness of operatic modules. It relies on a very simple fact. Let F and G be two linear species. And let me assume two things. Assume that, first of all, F and G are reduced. So there is nothing in arity 0, no constants, if those species are underlying linear species of some operands. And that if you look at arity 1, if you look at, again, in the operatic context, operations with one argument, then you just have a one-dimensional vector space. So in every operand, you have at least one-dimensional vector space of unary operations. You have the identity operation, which is defined for any signature. And I am assuming that there were no other unary operations, essentially. And that the dimension of f of I is equal to the dimension of g of I is equal to 1 for every finite set of cardinality 1. Yes, so I tend to call such things connected because somehow, for me, I think of so the identity operation inside an operand. It's an analog of the unit of an associative algebra. So an associative algebra, a graded associative algebra with just a ground field in degree 0 is often called connected. So I tend to call such things connected. So although a lot of people who do operands entirely in the context of algebraic topology will somehow use the word connected and reduced in a slightly different way in this context. So I remember on Math Overflow, there was some question about operands, and there was some, Peter May, one of the inventors of operands, left some comments indicating that he was quite unhappy with some terminological choices in that question. So yeah, but... Right. Yes. So in any case, so I make these assumptions. I mean, for the statement that I'm going to give, the second assumption can be made a little, can be relaxed a little bit. I think that the result I'm going to state will be true if for these components for one element finite set are finite dimensional, but I'm not going to bother myself with that. So then then if we denote if for any species Q by the, we consider the exponential generating function for dimensions. So the dimension of Q of 1 to n divided by n factorial to the power n. So for each species Q, I consider just some such formal power series. We have that the generating function of the composite F circle G is the composition of the corresponding generating functions for F and G. So the composition, the composite product of species corresponds to substitution of power series into each other. And this is, in some sense, the way, so I'm not going to give you a proof of the sort right now. In some sense, in the context of linear species, it's considered to be a very standard fact. And to be honest with you, this is, I think, as far as I understand the historical context, this is the way, how André Joyal invented species in 1980s. So his idea was to somehow give some kind of categorical context to categorify substitution of power series, and he invented that beautiful formalism of species, which somehow tells you on the level on some. So this is the note. So I define for every species the generating function for dimensions of components, and so I am saying that the generating function for the composite product is the composition of the corresponding generating functions. So in particular, if O is an operand and M is, say, a right O module, then I claim the following, that if you take, and then if M is free, then the exponential generating function for M composed with the compositional inverse of the generating function for O has non-negative coefficients. Indeed. Yes, this is compositional inverse. So formal power series form with starting from T form a group under composition. This so they have constant term. They have constant term 0, and the coefficient of T is equal to 1. So they start with T. So they are they form a group under composition series like that. Because if they start with 1, yes, then it will be so-called this composition is a operation. No, if they start with from constant, you can multiply them. You cannot compose them. You can.
superposition. Superposition, so it's so-called not in K group.
No, but this is what I mean. When I mean composition, I mean, yes, substitution into, yes. So there is just, there is just, yeah.
It will be a group.
Yes, exactly. Yeah, that's what I'm saying. That's exactly the inverse with respect to that. Yeah.
But it's, for this they have to have, I think a constant term should be 1.
No, constant term is 0. Because if the constant term is 1, you cannot compose you will, yeah.
So exactly, this is,
yeah.
So this is product composition operations correspond to product in this group.
Yes, exactly. Yes. So indeed, if M is free, M as a species is isomorphic to the composite product of Z and O for some species Z. So Fm of T is equal to Fz of Fo of T, and applying inverses, you see that this composite Fm with Fo inverse is just the generating function for dimensions of Z, so it does have no negative coefficient. So that's a very cheap test for freeness. Let me immediately apply it. Example. Let's take the following pair of varieties. The variety of alternative algebras, so algebras for which the associator is completely antisymmetric in its arguments. And so it is well known that if you take an alternative algebra, then the operation AB minus BA, well, it's not a Lie algebra, but it satisfies the axiom of called Maltsev algebra. And I'm not going to reproduce the axioms on the board. I will give you the first dimensions of components of the corresponding operand. So let me put alternative, Maltsev, and let me here put number of arguments 1, 2, 3, 4 will be enough. So here we have 1 because there is only one unary operation. Here we have 2 because alternative operations, alternative has no symmetries, and here we have 1 because we take the only operation AB minus BA if you want. Here we have 7, right? Because we would have 6 for the associative, but alternatives are not quite associative. The associator is just completely antisymmetric, so you have 1 extra dimension of freedom. Here you have 3, because the Maltsev identity is the identity with 4 arguments. On the monomials of 3 arguments, you still have no dependencies. And the last one, it's a little bit harder, so you need some little calculation to do. So I suggest that you trust me that the dimensions are 32 and 12. So the multilinear alternative operations with 4 arguments, the space has dimension 32. Multilinear Maltsev, so the S4 module generated by the Maltsev identity is 3-dimensional. There are altogether 15 multilinear elements in the free anti-commutative algebra, so 15 minus 3 is 12. So we compute the F alternative composed with F Maltsev inverse, and this is a computation which I did by hand this morning. It doesn't even require up to, if you only care about things up to degree 4, you can do it by hand without much trouble. And you get t plus t squared over 2 plus t cubed over 6 minus t to the power 4 over 24, and then something with degree 5 and higher. And this little calculation immediately shows that these two varieties do not form a PBW pair. Probably it was already known, but somehow this is an example of how something like that can be justified by a very straightforward, very easy computation. So somehow, and of course, well, since in the context of PBW theorems, freeness of the right module was important, I gave you this criterion for the right module, but of course there is a similar criterion for freeness of left module, where you need to pre-compose with the inverse, not post-compose. So there is an analog, an obvious analogs for left modules. And just to remind you what I was saying yesterday, that freeness of left modules, it's also useful for something, just for something else. So if you have a morphism of operands for which the target is a free left module over source, this would mean that, so morphism, let's say from P to Q, this means that freeness of a left module means that free Q algebras are free when considered as P algebras. So for example, yesterday we saw that free pre-Lie algebras are free when considered as Lie algebras. So in principle, it is also...
Excuse me, can you repeat this means?
So if you have a map of operands and Q is free as a left P module, then free Q algebras are free as P algebras. So this is also, in principle, sometimes leads to some interesting consequences for varieties of algebras. Yes.
More questions. You know that a pair of variety is not a PBW pair if at least one of two conditions doesn't satisfy it. Or there is no, say, injection of free, or injection have the injection, but how to say, we can have two algebras of the same dimension. Which
Yes.
When we know exactly what this happens, in which can we somehow from this found examples of when algebras in variety when
that's yeah, that's a good question. I mean, yes, no, I mean, to moving from making a conclusion like that by this numerical test to some concrete examples of failing of the PW property, that's a completely separate question. Yes, of course, well, a calculation like that is too primitive in a sense to give you some powerful.
To give some idea where we have to look, for example, or some.
Okay, well, if I can speculate, I would say the following: there is a very powerful generalization of this formula, which I am not going to write on the board, which so this formula tells you something about the relationship of dimensions, right? There is a very powerful generalization of this formula, which gives you relationships between characters of symmetric group acting on all these spaces. If you find some sort of contradictions on that level, that can be sufficiently suggestive because you can somehow look at appropriate isotypic components and try to figure out what. So that kind of computation can be useful perhaps for guessing some examples, but that's as much as I'm going to say now. Yeah. Yes. Yes.
Here, the composition of two polynomials correspond to the product of operands.
Yes.
Is there some interpretation for algebras composition of two Hilbert series?
Well, for algebras, for the product of Hilbert series corresponds to the tensor product of algebras. Yes. Yes, but superposition, there is the problem, because for algebras you usually have the constant term, and if you have the constant term, you cannot substitute things into one another in the ring of formal power series. So that's the problem. So, but now this was a very
take only a known, you forget the identity, no unitary.
Yes. Well, okay. There are. Okay. Let me put it like that. There is one possibly reasonable answer to this question that goes in the following way. There is actually a certain. So about 7-8 years ago, I defined a certain functor that takes a non-negatively graded algebra and constructs an operad out of it. It does well. Actually, I defined two different functors, and one doesn't really. Actually, it's very good because it doesn't change dimensions. It does something. It creates a lot of new structure, but it doesn't change dimensions. And somehow there is a way to move from the universe of graded algebras to the universe of operads, and then suddenly, of course, things like composing series start making sense. But I never looked at it precisely. But so possibly there is something. Let's yeah.
You can consider, for instance, free one-generated algebras without union.
Yes.
Varieties.
Yes.
All these algebras would be of this type.
Yes, I agree. I agree, but no. But I think that it's fair to say that whenever you see composition of power series and you want to interpret it, well, yeah, compositions of formal power series usually comes from this Royale's approach, you should somehow have some linear species and composite product of linear species. So if you just have an algebra, it's kind of not enough. You need to push your algebra into the universe of linear species first. That's what I'm...
Maybe the question is, if you consider the result, there exists a free algebra in some variety of this function?
That is certainly a very relevant question, and there have been recently some very interesting work in that direction. So somehow, for example, James Zhang with his collaborators, they started looking at possible sort of Hilbert series of various operands, and they proved some analog of Bergman's gap there, and so they started developing it somewhat systematically. So currently there are some things going in that direction, but it's tricky. It's tricky. Okay, so let me see what I want to erase. Somehow I want to mention before I explain somehow the very last in the context of this mini course, the very last application of techniques of shuffle operas, I want to elaborate, to talk a little bit more about the species, about the construction, the derivative of the species that I started explaining yesterday in the context of multiplicative, universal multiplicative developing algebras. So yesterday, I explained to you that if you have an operand O, then you can construct D of O, which is kind of you start regarding one of the inputs of the operation as some considered to play a special role. And in principle, of course, you can do it for any species, but the structures that you obtain are much richer if you start from an operand. And if you start from an operand, D of O becomes a right O module. And also I was saying that it has some sort of associative product. And I want to elaborate a little bit more as to what exactly I mean by that associative product. So intuitively, I explained to you what we do. If we have two different things with one special input, we can substitute one in the special input of the other, and that's fine. But let me explain to you what exactly I mean, because this is related to another monoidal structure on the category of species. So another monoidal structure on the category of linear species, which is called the Cauchy product. Because the composite product, as we saw, categorifies the substitution of formal power series. The Cauchy product categorifies the Cauchy product of formal power series, the product of formal power series. And so somehow it's denoted usually just by the tensor product sign. So if you have two species f and g, their Cauchy product, evaluated on a finite set I, is given by the following formula: direct sum over all ways to represent I as a disjoint union of j and k, f of j times g of k. A very nice and simple formula, much simpler than what we had in the context of the composite product. And if you think about it, you will see that, so remark that this Hilbert series of the Cauchy product is just always no assumptions needed, well, except for perhaps fine dimensionality of components, just the product of the series. So dividing by factorials will create some binomial coefficients, and those binomial coefficients precisely control the decomposition into disjoint union, so everything works out quite nicely.
So then the product is not already connected.
This tensor product might, for
This square.
no, but for example, so here there are no assumptions. It can have something with arity 0. It can this works always. So even without a reduced or connected assumption. So for example, if O is a reduced connected operand, then D of O, this construction, it's not going to be reduced. It will have something in arity 0, because D of O in arity 0, it's O with one special input added. So is no longer reduced, just as a remark. Now, just to emphasize that this, so let me just say that the linear species equipped with the Cauchy product form a symmetric monoidal category with the unit, let me denote it, so I will put this letter I. So I put like I used 1 like that for the unit of the composite product, and this this is just on each finite set. It's 0 if your finite set is non-empty, and is the ground field if I is the empty set. So for the Cauchy product, the unit should be the ground field support that the empty set, which is logical, right? Because for the formal power series under multiplication, the unit is just a constant power series equal to 1. So you want something supported in the empty set. All right, and the associative product on D of O that I mentioned yesterday, it's speaking precisely, it's just the structure of an monoid in this monoidal category. Why is it like that? Let me draw a little picture to perhaps convince you of this. So suppose that we have, so this is going to be d of O of some element belonging to d of O of I, some element belonging to d of O of j. What does it mean, d of O of I? It's an element of O with the input set I and the element star. So here we have I, here we have star. We have another element of O of d of O of j, so it's an element of O with the set of inputs j and the special element star. And when we compose these elements, we substitute this one into the special input of the other one. What do we get as the result? We get star and we get the total set of inputs, which is precisely this joint union of I and j. And maybe if you allow me to quickly change to match what is written there, let me call this j and k. And this is precisely the structure of a monoid in this monoidal category. For each way to split the total set of inputs I into j union with k, you have a composition of this sort, or a product of this sort. So this way we get, this is the monoid structure. So the monoid structure, it's the, we need an operation like that, right? This would be a structure of a monoid in our monoidal category. So it's the direct sum d of O of j, d of O of k to d of O of I, where I is the disjoint union of j and k. And this picture tells you that the definition that I gave you yesterday does precisely that. And its associativity of this product follows from the properties of the that happens in the operad. So somehow this is, I don't know. To be honest with you, so my intuition of working with operads is often much more developed than intuition from varieties of algebras. So when I think about universal multiplicative enveloping algebras, this is what pops up in my head first. I don't think about universal multiplicative envelopes directly at times. It all starts from there. Okay, now we are very close to, well, to the end of the mini course, but also to the very last topic that I wanted to discuss in this context. Because somehow the two applications that we already saw, that we saw for now, the two types of PBW theorems for the in the context of functors of changing multiplications, in the context of multiplicative enveloping algebras, it was all the same. It was freeness of the right module, and okay, there are methods. Let me show you one more example. And So let me ask the following question: when for which varieties of algebras the universal multiplicative envelope of a free algebra is free as an associative algebra. So, first of all, before I will tell you in a second why this question is potentially interesting, but first of all, it's the type of question where the operad theory can be potentially useful and promising. Why? Since the operad theory usually tells us in the context of varieties, look at, study multilinear operations that you can define. This means that we don't have tools to attack one concrete algebra in your variety. We don't have methods to study your favorite algebra. We have methods to study questions that can be formulated intrinsically for the variety itself. And this is an example of a question like that. Universal multiplicative envelope of every free algebra is free. It's property of variety. It's not property of some special, wonderful, exceptional algebras in that variety. And that is, so potentially we might have methods for this. Now, let me give you a couple of examples what happens in varieties that we know and understand. So, if we take the variety of Lie algebra, this property is true. The universal multiplicative envelope of the free Lie algebra is the free associative algebra on the same generators, actually. But that happens because of some funny coincidence. Remember what I told you yesterday, that for Lie algebras, there is this bizarre magical coincidence. There are two different universal envelopes. So there is the pair associative and Lie, which are related by the functor of change multiplication. And so for each Lie algebra, you have its universal enveloping associative algebra in this sense. And you have the multiplicative universal envelopes of Lie algebras. And those two universal envelopes constructions happen to be isomorphic. This means that the universal multiplicative envelope of Lie algebra happens to be a left-adjoint functor. And so the universal multiplicative envelope of the free Lie algebra must be free because you compose two left adjoints, you get a left adjoint. So this is what I mean, that this is true in some sense by coincidence. Another example that would be useful to have in mind is to look at the variety of all associative algebras. Let's say unital associative algebras. In this case, the universal multiplicative envelope, everyone who heard, for example, everyone who heard the definition of Hochschild cohomology will immediately recognize the universal multiplicative envelope is the tensor product of an algebra A with its opposite algebra. So if an algebra A is a unital associative algebra, the universal multiplicative envelope of A is the tensor product of A times A opposite. in particular, the universal multiplicative envelope of the free associative algebra is very non-free, right? It has two commuting subalgebras, two commuting free subalgebras inside it. So this property is not automatic. Sometimes it holds, sometimes it doesn't. The reason, so my personal motivation is the following conjecture due to myself and Olbay Umerbaev, that this property is equivalent to the Nielsen Schreier property of a variety of algebras, which says that every subalgebra of every free algebra is free. Tomorrow at 4 o'clock, right, there will be a seminar where I will talk a little bit, well, I will talk about a new way to look at the Nielsen Schreier property in the case of Lie algebras, and I will maybe say a few more words about this conjecture, but for now I just mention it as a motivation. Yes?
The seminar of the group of representation that I and Costa every Friday and before.
Yes. And okay, so somehow this is so this is the motivation for this property. Now let me tell you how to test this property using shuffle operas and Grobner basis for operas, and that will be somehow the last serious result that we will see in this mini course. So a criterion using shuffle operas. And before I state this criterion, let me remind you what happens in the case of Lie algebras, where we already know what that the Jacobi identity forms a Grobner basis. So for Lie algebras, so we have the Jacobi identity written in the universe of shuffle operas like that. The shuffle Jacobi identity. We know that we can choose an ordering of monomials for which this guy is the leading term. The only tree growing to the right is the leading term. So we have normal forms all trees growing to the left, where the only condition, the condition coming from the shuffle tree combinatorics, is that the minimal leaf is the extreme left leaf, and everything else is absolutely arbitrary. So these are normal forms. There are, of course, n-1 factorial of them, all permutations here. And I suggest to observe that this combinatorics, it's so now we move to the universal envelope, move to the D of Lie. So here, well, the only thing that we need to do is to say that now this input we declared as the special input. So I said last time in the universe of shuffle operas, we always make the smallest input the special input in the deconstruction. And here, I1, In-1. And now I suggest to observe that this is the free monoid generated by this particular element. Well, let me call it 1, so there is a star and 1. Why? So when we do this Cauchy product, we for this D of O, we iterate substitutions in the star slot, and the Cauchy product, when we form the free monoid, every time we consider we do all possible splittings of G and K. So when this means that in the free monoid generated by this, you will have these elements 1, 2, and 2, 1, because the total set of inputs 1 and 2, you can split into 2 parts in 2 different ways. First 1, then 2, first 2, then 1. So you have both of these. Then you multiply this in this monoidal category by the same thing, and you will get 1, 2, 3, 1, 3, 2, and so on. You will have all possible 6 things, because again, you need to use all possible splittings in several parts, and so on and so forth. So the construction of the free monoid generated by this guy precisely gives you all possible permutations of arguments here. So somehow, using Grobner basis, using normal forms for this particular Grobner basis, we established that in the universe in the shuffle worlds, this monoid is free. And then we use the usual trick that I already alluded to several times, that for properties like freeness of a module, checking it in the universe of species, in the universe of operas and the universe of shuffle operas, it's the same, because there are some homological criteria, so you can somehow freely move between the two universes. So this is a very short argument showing that, another argument showing that the universal multiplicative envelopes of freely algebras are free, which is kind of, I think, in some sense, it's more conceptual. So here there was some coincidence, okay, the universal multiplicative happened to be left adjoint, so yeah, here it kind of explains what exactly happens. And general result, and this will be the last thing that I state. The result, let us fix an ordering for which, well, similar to this one, an ordering for which trees growing to the right are bigger than trees growing to the left. Again, it's possible to formalize, I mentioned it briefly in Coichiba, there are some, well, maybe, yeah, I think there are some hints already in the existing preliminary lecture notes. So fix an ordering for which trees growing to the right are bigger than trees growing to the left. Suppose that an operad O is such that the shuffle operad O AU has a Grobner basis with all leading terms like this, with the all leading terms where the minimal leaf is directly connected to the root of the tree. Then universal multiplicative envelopes of free or algebras are free. And in fact, this is an if and only if result. If for such an ordering the Grobner basis is of different shape, then in general universal multiplicative envelopes are not free. So in fact, it's possible to upgrade it to a proper criterion, to an if and only if result. And this this is very helpful. As I mentioned, for now, this conjecture is, well, a conjecture, but we developed some methods. We managed to give some slightly more technical condition using operatic Grobner basis to give a method, to establish a method of proving the Nielsen Schreier property. And for example, the variety that I mentioned many times during this mini course, the pre-Lie algebras, the right symmetric algebras, satisfy that Nielsen Schreier property that subalgebras of free pre-Lie algebras are free, and this is a new result, not only new, a sufficiently surprising result. So, for example, while Bauman, Baev, and I, when we started working on this circle of questions, he was completely sure that pre-Lie algebras is not a Nielsen Schreier variety, to the extent that he had actually a candidate of a counterexample found by one of his students about 10 years ago, and so this certainly was a big surprise when we figured this out. All right, so I think that all in all, I tried to give you enough indications of how this viewpoint and the methods that arise from this viewpoint can be actually useful in the context of algebras with polynomial identities, and perhaps I gave you some examples that were instructional enough that you might want in the near future to take some variety of algebras that you like and test something about that. If that happens, that would bring me a lot of happiness. Don't hesitate to let me know if that happens, and I'll thank you and stop here.
Okay. Thank you very much again.
Yeah.